So let's proceed further with the valid examples to have a clear idea how the subtraction with complements can be executed. Examples to illustrate the procedure. Now first we'll start up with the two binary numbers. Let us say x, which is 1 0 0 1 0 1 0 1 0 0, and y, which is 1 0 0 0 0 1 1. So the performing first operation will be subtraction, that is x minus y, and the second one will be y minus x. Okay, so the first procedure will be by 2's complement, that is 1 0 1 0 1 0 0 1 0 0 0 0 1 1. So first we have to find out the 2's complement of this number, which will go as follows. 1, which is the first one. As we all remember, the procedure to obtain the 2's complement is we have to write the number as it is from right to left till we get the first one. After getting the first one, we have to replace 1 by zeros and zeros by 1. So this is the first one. This is what we were looking for. Writing this one as it is. Now replace all ones by zeros and zeros by 1 from this bit onwards. 1 by 0, 0 by 1, 0 by 1, replace 0 by 1, replace this 0 by 1, and replace 1 by 0. This is the 2's complement of y. Now step number 2. Adding the 2's complement of y to the binary number of x. The sum gives 1 0 0 1 0 0 1. Now as we can see, this 1 carry, the last bit is having this 1 carry. Okay, in 2's complement, if there is 1's carry, then it means that the number or the final result is negative, and that is the reason we take the entire 2's complement of this number. Okay, since the number what we obtain here is minus 1, sorry, the number what we obtain here is 1, that is the end result is carry. Okay, so the step here we'll be doing is 1 shows negative. That is the reason we are getting here negative, as there is 1 in 2's complement. In 2's complement, 1 often denotes 0, 1 often denotes minus. So that is the reason we getting a minus sign at this place, and the answer x minus y is 0 0 1, which is this number 0 0 1 0 0 0 1. That is, the sum is this. Now let's move on to the other example, y minus x, which is 1 0 0 0 1 1 0 1 minus 1 0 1 0 1 0 0. So we have to execute this procedure itself by 2's complement. So let's take first 1y. Why this value? 1 0 0 0 1 1. Find out the 2's complement by the procedure. Sorry, we have to find out the 2's complement for x, for this number 1 0 1 0 1 0 as 0 1 0 0, as this number is to be subtracted from y. The 2's complement for x can be found out as 0, so there is no 1, this is 0. Again we have not found out first one. Now here comes the first one, that is we can write these 3 bits as it is here, and then we start replacing all zeros by 1, 1 by zeros. So we can see this 0 1 0. So after adding x plus y, we can find out the sum is 1 1 0 1 1 1 1. Since there is no end carry, that is the end carry here is 0, the answer y minus x is equal to minus of 2's complement. That is, the answer here is we have to take minus. Okay, we have to take here minus, and then we have to start finding the complement of 2 for the final result. That is, since 0 here, 0 represents negative in this case, therefore 1 is written directly 1, 1 is replaced by 0, 1 is replaced by 0, 1 is replaced by 0, 0 is replaced by 1, and 1 is replaced by 0. That is, This is the first one, so we have put on the one as it is. After this, in 2's complement, we replace all 1's by 0 and 0's by 1. So we replace 1 by 0, 1 by 0, 1 by 0 and 0 by 1 and so on. So now the next step, numeric codes. In numeric codes, there are different kinds of codes: binary codes, BCD code, ASCII codes. Why do we need to study the codes? What are the scopes of this code? Why are we studying this? The most important use of the codes, either it's a binary codes, weighted codes, BCD code, ASCII codes, is that they represent the bits 1, 0, or their value represents a very important factor in digital systems as well as in computer systems. So let's start up with the first code, which is binary code. Binary codes are the codes which are represented in binary systems with modification from original ones. That is, the binary codes are the same codes like the binary numbers, but they are represented in binary systems which are modified from the original ones. So we'll have a detailed look on this. Before this, let's check out binary codes, types of binary codes, and what are the things that we can look into this binary codes. First, binary codes. First type is weighted binary codes, and the second one is non-weighted binary codes. So the first type of weighted binary codes are those which obey the positional weighting principles, and each position of the number represents a specific weight. That is, as we have seen previously, like in binary systems, we multiply to the increasing power of 2. That is 2 raised to 0 for LSB, 2 raised to 1, 2 raised to 2, and so on. Similarly, in weighted binary system, also each bit is having its own weight. Therefore, named as weighted binary systems. Now, again, there are different types of weighted binary systems which can be classified as 8-4 to 1, 2-4 to 1, 5-4 to 1, 5-2-1, and so on. So these are the types of weighted binary codes, and let's check out the representation of binary codes, their equivalent binary codes and their counterparts. As we can see from this, 8-4 to 1, okay, 1, that is 2 raised to 0, 2, that is 2 raised to 1, 4, that is 2 raised to 2, and 8, again, that is 2 raised to 3. That is the reason the weighted binary systems start from 0 to 8, from 0 to 9, and we can check out their equivalent systems. Let's say, for example, for 9 is represented as 1001. As we have discussed previously, that binary systems are the modified representation of binaries. We can check out this 9, which is again represented in the similar way of what we represent the decimal line to equivalent binary. How the 9 is obtained? This is 1 into 2 raised to 0 plus 1 into 2 raised to 3, that is 8 plus 1, which gives 9. Similarly, 2-4 to 1 and 5-2-1. Before moving on to this, let's study the XS3 code, which are of course a very interesting kind of codes, and the most simplest code after 8-4 to 1, I can say. XS3 code, if we check this number and its equivalent decimal number, it doesn't make any sense. Like, we often get confused. This represents decimal 3. You can check out 3, and this represents 3. This one in XS3 represents 4 in decimal 4. Similarly, 3 in XS3 is represented as 6. So from this comparison, we come to conclusion that XS3 codes are those codes which are obtained by adding 3 to the original decimal number. That is, for example, if 0 is added with 3, that is 0 plus 3, we get the XS3 code 0011, which corresponds to 0 in XS3 system. If we add 1 plus 3, that is, if we add the binary equivalent of 0001 to 3, we get its binary equivalent of 4. Similarly, if we add 2 plus 3, we get the x3 equivalent of 2 is 0101, which corresponds to the x3, which corresponds to the decimal or binary equivalent of 5. Hence, x3 code are obtained by adding 3 to the existing decimal or the existing binary numbers. And the x3 codes start from 0 and end up at 9 for the decimal equivalents. That is, the valid x3 codes on its original account, they are from 3. We can check out from this 0011, which corresponds to 3. They start from 3 and end to 12. So the valid x3 code from 3 to 12, and the invalid x code are 0, 1, 2, followed by 13, 14 and 15. Now we'll check out with the 8421 code, also called as BCD code. BCD code or binary coded decimal is a straight assignment of the binary equivalent. That is, it is possible to assign weights to the binary bits according to their positions. As we have discussed here, 8421, these are the weighted codes. Like if we have to find out 1, that is, if we have to write down the equivalent of 1, then we write 1, which is 2 raised to 0. If we have to find out 2, then we write it here 1, which is 1 into 2 raised to 1. Similarly, to find out 8, we write as 1 into 2 raised to 8. So, as it is clear from the above example that the BCD codes are the weighted codes. Now, the example, we can see the bit assignment of 1009, which corresponds to 9, as its weight can be seen by the decimal representation. And this is the calculation how 9 is obtained. 1 into 2 raised to 0, which gives this 1, plus 0 into 2 raised to 1, which gives this 2, plus 0 into 2 raised to 2, which gives this 4, plus 1 into 2 raised to 3, which gives 9. Similarly, the number 12 is represented in BCD as this way, which is the decimal equivalent of 1, and this is the decimal equivalent of 2. Now, why 12 is represented in this way and why not in the regular decimal shape? It's because the valid BCD codes are from 0 to 9. After 9, we take the numbers individually with their corresponding binary codes. Hence, 12 is represented in this way.